Everybody. We're going to be doing the seasons review questions part 2. Basic answers to questions 1 through 4 on the diagram below, which represents the sun's apparent path and solar noon positions for an observer at 42 degrees latitude on December 21st, September 23rd, and June 21st. I personally just like to highlight latitudes anytime I'm doing seasons questions. Just to give me an idea, since latitudes plays a major role in how much daylight hours we have, etc., things of that nature. So it says, in which direction will sunrise occur on June 21st? So I'm going to look at June 21st here. And even though there aren't any,
I'm sorry.
even though there aren't any arrows, even though there aren't any arrows, we know that the sun generally rises from the east, right? It travels upwards and it sets towards the west, right? So that means the sun rises right at this point, right? Right at the horizon. And let me make sure this says sunrise. And what do I know? This point is between N and E. So therefore, which direction will the sunrise occurs on June 21st? If it's between north and east, it will be northeast. All right. One thing just to keep in mind, all right, you do want to remember, and this is on page 6 of the review sheet, where you do want to memorize, depending on the dates that are given, where does the sun rise from which direction? So if it's the equinox date, it rises on the east and sets in the west. If it's the winter solstice date, the sun rises southeast and sets southwest. If it's the summer solstice date, the sun rises northeast and sets northwest. So that's just something you have to keep that in mind. All right, let's take a look at number 2, right? Using that same diagram. Which graph best shows the altitude of the sun as measured by an observer located at 42 degrees north at various times on December 21st? All right. So we know 42 degrees north is still consists of New York State. All right, so that's something to keep in mind. And we know that on December 21st, that is also the winter solstice. And I don't know if you guys remember the lab that we did, but do you remember when we filled in the chart on our review sheet? One thing that we've noticed, right? I want you to look at if you could even look on the screen. Look at the winter solstice date. Look at the duration of insolation. And we're only going to focus on the latitudes that's above the equator, that's in the northern hemisphere. And one pattern that you'll realize is that during the winter solstice, all latitudes above the equator, they have less than 12 hours of daylight. Less than 12 hours of daylight. Now, why is that important? Because now we're going to break down each chart. There's a couple things I see that is wrong. Number one, we are in New York, right? And in the latitude 42 degrees, the sun never reaches a 90 degree angle at solar noon. We never receive that. We never receive that in New York. All right. As a matter of fact, you could even check to see if you go to let's take a look. Go to page 2 real quick, and you feel free to pause, rewind. The only areas that actually receive 90-degree vertical rays from the sun is any latitude that's less than 23.5 degrees north, all the way to less than 23.5 degrees south.
Hello?
If they don't fit that range, then therefore,
Hello?
if they don't fit that range, then therefore it will not receive direct sun rays. Yes. So therefore, New York, for example, is going to be outside of that range. So that's why New York won't receive 90-degree sun rays, right? The other issue that I have with diagram A is that the sun rises at 6 a.m. and it sets at 6 p.m. How many hours is it from 6 a.m. to 6 p.m.? 12 hours. And we know the only day or days out of the years where New York will receive 12 hours of daylight is only going to be during the equinox. So that's why A can't be the answer, right? Now, C, right? One thing you'll notice, the altitude of the sun never touches zero. So that means at location C, the sun is up for 24 hours. All right. Now, when I'm looking at D, right, number one is going to be less than 12 hours of daylight. Less than 12 hours of daylight, right? And the noon sun does not reach 90 degrees. And so these two things works out for me as to why the correct answer would be D. The sun is up for less than 12 hours, and the noon sun does not touch 90 degrees. So that's why D is going to be a correct answer. All right, so if we look at number 3, how many hours occurred between sunrise and solar noon on September 23rd, right? So one thing we know, September 23rd is what? That is an equinox date. Why is that important? It's because at an equinox, all latitude receive the same equal amount of hours, right? All latitudes receive 12 hours of daylight, right? What does that mean? It takes 12 hours to go from sunrise to sunset. You with me now? All right. So that means when I look at my diagram, it took the sun 12 hours. It took the sun 12 hours. It took the sun 12 hours to go rising at the east and setting in the west, right? To go from sunrise to sunset. Took 12 hours. The question only asked how many hours occurred between sunrise and solar noon. So if it took 12 hours to complete the cycle, then that means it only took 6 hours to go from sunrise to solar noon, right? If a full cycle takes 12 hours, half that cycle to go from sunrise to solar noon is only going to take 6 hours. And that's why the correct answer is going to be choice A, 6 hours. All right, number 4. Which diagram best shows the location of Polaris relative to the observer, right? Well, let's take a look. Remember that Polaris is equal to our latitude. Remember that? So if my latitude is 42 degrees north, then that means the altitude of Polaris is also going to be 42.
Hello?
So yes, so the altitude of Polaris is also going to be 42 degrees. And Polaris has to be located towards the north side. So therefore, I'm going to choose an option that has, Polaris at a 42-degree angle and located towards the north side, right? It can't be A because Polaris is at a 0-degree angle, and it can't be C because Polaris is located, it's saying that it's located towards the south side where the sun is, and that is incorrect. Is going to be choice B because Polaris looks to be about a 42-degree angle and is located towards the north side of the sky. All right, number 5. It says basic answers to questions 5 and 6 on the diagram and data table below. The diagram represents the sun's apparent path as viewed by an observer located at 50 degrees latitude north on June 21st and March 21st. The data table shows the sun's maximum altitude for the same 2 dates of the year. The sun's maximum altitude for December 21st has been left blank. Number 5. Which statement best compares the intensity and angle of insolation at noon on March 21st and June 21st? Remember the rule, right? As look at page 2, we said it right here. The higher the sun angle, the more intense sunlight there is. There's a direct relationship. That's why the lower the sun angle, the less intense sunlight there is, right? Meaning that there's less energy being received from the sun. So therefore, what statement can be best compared? The intensity and angle of insolation at noon on March 21st and June 21st? Well, June 21st, the sun is at a higher angle on June 21st than March 21st, right? Do we see that? The sun's at a higher angle at June 21st compared to March 21st. So that means the intensity and the angle has to be greatest, right, on June 21st. It's not going to be on March 21st because June 21st angle of insolation is higher, right? It's not going to be mixed up like choice 3 and choice 4. If you have the higher angle of insolation, you will have the higher intensity of insolation. And that's why the correct answer is choice 2. 6A, calculate the sun's maximum altitude on December 21st on the chart. Well, because of the Earth's tilt, let me go ahead. All right, because of the Earth's tilt, right, the Earth's tilt at an angle of 23.5 degrees. In our diagram, if we turn all the way to page 6, all right, you can take a look right here. You'll notice that the difference in angle between June 21st and March 21st is 23.5 degrees. That means that December 21st solar noon position is going to be 23.5 degrees lower than March 21st or September 21st, right? Noon sun altitude. So therefore, if you look at the pattern, these two are 23.5 degrees apart from each other. So therefore, to find December 21st angle, I'm going to take 40 and I'm going to subtract it by 23.5. And when I do that, 40 minus 23.5 is going to give me 16.5 degrees. So 16.5 degrees. All right, 6B. On the diagram above, draw and label the path of the sun for December 21st and July 21st. For December 21st and July 21st. All right. So I'm going to start with December 21st. Remember in the previous problem, we found that the sun's maximum altitude is 16.5 degrees. So therefore, I'm going to look here and I'm look for 16.5 degrees, which when I zoom in, it looks to be somewhere around here. 16.5, somewhere around here. And you have to remember, right, that the sun rises southeast, right? So between south and east, draw my curve, and it sets between southwest, right here, between south and west. All right. And I'm going to label this December 21st. That's the first thing. All right. Now we took care of December. All right. The sun rises southeast, it sets southwest. Now, the next thing that we're going to do, I took care of that already, is July 21st. Now, July 21st, we're going to sketch it, right? If we look at the pattern, it goes December, January, February, March, April, May, June. This date is the highest that the sun's path will ever be throughout the year. So after June 21st, the path will begin to go down again. So July is going to be somewhere around here because it's going to be June. Follow my pencil. July, August, September, right? Because March 21st and September 21st are in the same position. October, November, December, January, February, March, April, May, June, and July will be right here. So I'm going to make my solar noon for July, and it's going to be between that June 21st and September 21st, right here. All right, and I'll label this July 21st. Number 7, base the answer to the following question on the diagram below, which represents a model of the sky, celestial field for an observer in New York State. The curved arrow represents the sun's apparent path for part of one day. The altitude of Polaris is also indicated. Now, what's interesting, you see how solar noon is located towards the south side and Polaris is located towards the north, okay? That always has to be the case. Polaris cannot be on the same side as where solar noon is going to be. Solar noon is always going to be towards the south side, towards the south side. All right? On which date could this observation of the sun's apparent path have been made? When you get a question like this, always look where the sun rises and where the sun sets. The sun is rising right here, directly east, and it's setting directly west. There's only one date where the sun will rise directly east and sets directly west in New York State. When we look at our notes, right here, let me clear this out. The sun rises directly east and sets directly west on September 21st and March 21st, also known as the equinox date. So during the equinox, the sun rises directly east and sets directly west. So therefore, the correct answer is going to be choice 1. Number 8, which graph best represents the average monthly temperatures for 1 year at a location in the southern hemisphere, right? Well, on our notes, we learned something very interesting about seasons that happen in the northern hemisphere, that's above the equator, and seasons that are in the southern hemisphere below the equator. When you're looking, look what we see. The seasons are completely opposite of each other at every position of the earth. When it's summer in the north, it's winter in the south. When it's winter in the north, it's summer in the south. So now I know my warmer temperatures, right, in the northern hemisphere is going to happen during the summer. And my cooler temperatures we know are going to occur during the winter in the southern hemisphere, right? So now that we know this, when I go back, right, because we're looking at the southern hemisphere, we have to think of the opposite. We have to think of the opposite. What do I mean? That means that during our warmest months in the northern hemisphere is going to be, right, June, July, and August, right? That's going to be for our warmest months. All right. Now, because the seasons is switched, in June, July, and August in the southern hemisphere, that's going to be their coldest months. Is going to be June, July, and August. So I got to pick a diagram where June, July, and August, they're going to have the coldest months. And December, January, February, they're going to have the warmest months, right? So C, all temperatures are the same. That's incorrect. And look at B and D. They have the warmest temperatures during June, July, and August. That's not going to work for the southern hemisphere. June, July, and August in the southern hemisphere has to be the coldest months. And that's why choice A is going to be the answer. Number 9, base your answers to question 9 and 10 on the latitude and longitude systems shown below. The map represents a part of the Earth's surface and its latitude longitude coordinates. Points A through F represents locations in this area. Number 9, points B and E have the same value of measurements of, well, B and E, right? What do they have the same value? Number 1, they're both at 60 degrees north. So I'm definitely going to circle latitude. Do they have the same time? No, they don't. Because they have different longitudes. B and E has different longitudes. So they're not going to be in the same time zones, especially when they're 40 longitudes degrees apart from each other. All right. Duration of solar day. If you have the same latitude, you have the same duration of solar day. If you look at our chart and you scroll all the way down to the last page, either page 7 or 8 for the chart, you'll notice, right, when anytime we plotted or we wrote down the duration of insolation, we only spoke about the latitudes, right? So whether you're 70 degrees north and 50 degrees west and 70 degrees north and 40 degrees west, you're going to experience the same duration of insolation. If you have the same latitude, you will have the same duration of insolation. All right? That's why this chart only has latitude to find out the different durations of insolation. All right? And not longitude. So therefore, you'll have the same duration of solar noon and the altitude of the sun at solar noon, right? If we take a look and we go to solar noon, you'll notice the altitude, observer's latitude is what matters. So as you can see, this line represents the complete latitude. It doesn't matter whether you're west or east of the world, right? Of the prime meridian. Look, we're still the noon sun stays the same for that entire latitude. Even if I change it to 48.4 degrees north, that means this entire latitude, whether it's degrees west or degrees east, will have the same altitude of the noon sun. And so it'll be A, C, and D. And, oh, sorry. Here we go. Number 10, points A and F have blank values of measurements of duration of insolation because they have the same blank altitude of the sun at solar noon. Well, A and F. Let me clear this out. Sorry. We're looking at number 10 now. A and F have different latitudes. Ding, 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 ding. If you have different latitudes, look what we just said about number 9, right? If you have different latitudes, then that means points A and F are going to have different values for the measurements of the duration of insolations. Different latitudes means you're going to have different hours of daylight. That's what the duration of insolation means. Hours of daylight. Because they have different altitude of the sun at solar noon. If you have different latitudes, then therefore you're going to have different hours of sunlight. When we did our lab, you can see right here, our duration of insolation, it does change. And of course, what's important, let me see real quick. Sorry. Latitude points represent the same values of, yes. 1, 2, 0, 2. All right. What's important that we see here, right, is the duration of insolation changes as your latitude changes, right? 80 degrees north compared to 30 degrees north, different durations of insolation. All right. Now, if this was the equinox, all latitudes have the same. But generally speaking, right, when you're changing your latitudes, you're definitely also going to change. Oh, sorry. Let me see sorry. You're going to change the altitude of the sun at solar noon. Take a look. Your latitude changes, and look at your angles. Your angles, the sun's angle at 12 p.m. noon also changes. All right. So that's something to keep in mind as well. All right, everybody. If you take a look at numbers 11 through 13, you can actually look at, for numbers, apologize, let me see, questions 11, 12, sorry, 11, 12, and 13. They're actually the same questions if you look on my previous video, positions of the sun's altitude questions. They're questions 8, number 9, and also number 6. So 6, 8, and 9 on my previous video, altitudes, questions of the altitude of the sun. You can watch those to answer numbers 11, 12, and 13. Number says basic answers to question 14 and 15 on the diagram below, which represents the apparent path of the sun observed at 4 locations on Earth's surface on March 21st. So make sure we highlight that. The present positions of the sun, Polaris, and the zenith, positioned directly overhead, are shown for an observer at each location. Number 14, explain why the intensity of sunlight at noon, right? Remember, guys, 12 p.m. on March 21st is greater at location C than than at the other locations. Well, I'm gonna look at location C, and 12 p.m. is when the sun is at the highest point, right? So I'm looking at 12 p.m. for location B, C, and A, right? And so therefore, look at all of these and you'll see which sun position is the highest and is going to be at location C. So why is it that the intensity of sunlight at noon at March 21st is greater at location C? It's simply because of the fact that the sun's altitude at location C is greater than the sun's altitude at solar noon, then the sun's altitude is greater than the sun's altitude at all the other locations at solar noon. All right. Remember, the intensity of sunlight is directly related to the altitude of the sun. The higher the altitude of the sun, the greater the intensity of sunlight. Number 15, state the approximate time of day for the observer at location B when the sun is at the position shown in the diagram. All right. So first things first, I'm going to zoom in here. All right. You see this point right here? Right when the sun reaches this point, right? The dome, the highest point, that's supposed to be solar noon, which is also known as 12 p.m. So we know where the sun is present location right now is going to be past 12 p.m. All right, we with me so far. The second thing is that this side is east, right? And this side is west. The fact that the sun, hold on. Matter of fact, let me, I don't even have to do all that. It tells us that this date is March 21st. What do I know? Talk to me, people. What do I know? March 21st is an equinox date, which means that this location has 12 hours of daylight, right? That means this entire path takes 12 hours to go from sunrise to sunset. Okay? That means if solar noon 12 p.m. is located here, sunrise is occurring at 6 a.m., sunset occurs at 6 p.m., right? During the equinox. And so therefore, what do I see? My sun's position is a little less than halfway between 12 p.m. and 6 p.m. So what is a good estimate? I would accept 2 p.m. or 3 p.m. as an answer. Because 6 p.m. is here, 12 p.m. is here, and the sun is a little less than halfway between 12 p.m. and 6 p.m. So therefore, I would accept 2 p.m. or 3 p.m. as an answer. Number 16, it says base your answers to questions 16 and 17 on the diagram below. Let me zoom in, which shows the angle of the sun's noontime rays received at different Earth's latitudes on May 1st. So this is how the Earth is positioned on May 1st. What changes can be expected to occur at 45 degrees north over the next 30 days, right? Well, that means over the next 30 days, that means what's supposed to occur from May 1st to, let's say, June 1st, right? Or you can say May 31st, it doesn't matter. What is supposed to happen? Well, what do I know? I do know that the sun is at the lowest point at December 21st. And the duration of insolation, the amount of daylight hours increase from December 21st to June 21st. That's what I do know. The duration of insolation increases constantly from December 21st to June 21st. So what does that tell me? From May 1st to June 1st, my daylight hours are going to increase. Daylight hours are going to increase. Are going to increase, right? What do I also know, right, is that the altitude of the sun, is going to increase. What does that also mean? The intensity of insolation will also increase. So my daylight hours are increasing. My altitude of the sun is going to increase, right? The sun's altitude is going to get higher and higher. Therefore, the intensity of insolation is going to increase, which means the energy that comes from the sun will increase. And if the energy that comes from the sun is going to increase, then of course, more energy from the sun means our temperatures are also going to increase. And what choice reflects all of that? Choice D. And the last question. At which latitude can the noontime sun be observed in the northern part of the sky? Can the noontime sun be observed in the northern part of the sky? At which latitude can the noontime... Hold on, guys. Give me a second. Hold on.